Okay, our second to last speaker for the day is Przezdziecki from the University of Edinburgh, who will tell us about an extension of Suzuki's functor to the critical level. Take it.
Thank you very much. By the way, this was excellent pronunciation of my surname.
I do my best.
Okay, so thank you very much for the invitation. So I'll start by recalling the fundamentals. So I'll start from some really basic things. So the fundamental building block of the Suzuki functor is the Schur-Wald duality, and I'll explain a little bit how it is related to this whole family of Arakawa-Suzuki type functors. Then I will talk about affine GLN and the Fagin-Frankel center, which is a phenomenon characteristic for the critical level. Then I'll talk about the rational Cherednik algebra and the Calogero-Moser space. Then I will briefly explain the construction and some basic properties of the Suzuki functor. And then I will explain how these two centers are related and some representation theoretic implications. Okay, so I don't know why some of the titles are black. It's some problem with the beamer, but I hope you can still see it. So this Arakawa-Suzuki functor, it comes from something very classical in representation theory, namely the Schur-Wald duality. So as we know, if we take the standard representation of the general linear Lie algebra and we tensor it m times with itself, then we have commuting actions of GLN and the symmetric group on this tensor product space. And Schur-Wald duality says that they centralize each other. And so we get a functor from the category of GLN modules to the category of modules over the symmetric group. And so we take a GLN module M, we tensor it with this bimodule, and then if we take the trivial isotypic component, and to express this in a slightly different language, this is the same thing as taking the space of GLN coinvariants. And this has been generalized to many more sophisticated settings. For example, well, I guess it all started with this paper of Arakawa and Suzuki, where they defined a family of functors from SLN modules to modules over the degenerate affine Hecke algebra. Later, this was upgraded to the affine setting. So there is a functor from affine SLN modules to modules over the trigonometric double affine Hecke algebra due to Arakawa, Suzuki, and Tsuchiya. And there is also a functor from affine GLN modules to the rational Daha, which was defined by Suzuki and later studied by Baragnolo and Passero. And so this third functor is what we're going to be interested in today. And so this actually, I would just like to make a remark that this has been a very popular topic in representation theory, and this has been taken in many, more recently, in many more, in many different directions. So there also exists a quantum analog of these functors, where you consider some quantum D modules on the left-hand side, and you get the full Daha on the other side. And there also exists some generalizations to type BC, where you consider, for example, quantum symmetric pairs on the left-hand side. But I mean, we're interested in this third functor here. And so now I'd like to say, make things a little bit more precise. So we are interested in the, not really the whole category of affine GLN modules, but the category of smooth modules of a certain fixed level kappa. And by smooth, I mean that if I take a vector in my module, then if I think of affine GLN as a central extension of power series in G, then I want sufficiently high powers of T to annihilate my vector. And so I let HT be the rational Cherednik algebra associated to the symmetric group and parameter t. And so this Suzuki functor, it goes from this category of smooth modules of level kappa to the category of modules of the Cherednik algebra, and we have a shift of the parameter by n. Suzuki and Varagnola-Vasserot, they studied this functor in the non-critical case. And under some mild assumptions on the parameters, it was shown that this functor induces an equivalence of quasi-hereditary categories between a certain subcategory of category O for affine GLN and category O for the rational Cherednik algebra. Of course, you have to take a subcategory here because this functor kills a lot of objects. And so the natural question is whether there exists a critical level limit of the Suzuki functor and what it's like and what it does. And so the new phenomenon which is present at the critical level and also when this parameter t for the Cherednik algebra equals 0 is that we have big centers. So in fact, the center of this category is trivial unless kappa is critical, and the center of the Cherednik algebra is trivial unless t equals 0. And so I should say maybe also in the Cherednik algebra there is a second parameter c, but since we're just working with the symmetric group, if I rescale the parameters simultaneously, I get an isomorphic algebra, so there's really just one parameter. I'd like to explain some motivations. So some of them come from integrable systems. So there is a connection between Calogero-Moser system and the KP hierarchy. And there is also work of Muhin, Tarasov, and Varchenko, who constructed this surjective homomorphism from the beta algebra of the Godin model associated to GLN to the center of the rational Cherednik algebra. And we also know that this beta algebra, so for instance, by the work of Chervov-Talalayev, is connected to the center of the completed universal enveloping algebra. So the goal here was to understand from a more algebraic perspective how these two centers are related. And there's also a hope, although at the moment it's quite a vague hope, that in the cyclotomic case, so the Cherednik algebra for the symmetric group, it's rather easy and we know almost everything about it, but this Cherednik algebra for the Reeve product at T0, there are still interesting questions to be asked, and there is a vague hope that maybe in the cyclotomic case, there's also a cyclotomic version of this functor. One could maybe say something, for instance, about the decomposition numbers. Okay, so now I'd like to say a few things about this Fagin-Frankel center. So we have the, so we know that the affine Lie algebra is the central extension, and since we're interested in modules of a fixed level, then we take this quotient of the universal enveloping algebra by the ideal generated by C minus kappa. And I'm interested in smooth modules, so I take a completion of my universal enveloping algebra with respect to this sequence of ideals. And it turns out that, that the center of this category is the same as the center of the completed universal enveloping algebra, and by a deep theorem of Fagin and Frankel, the spectrum of the center of this completed universal enveloping algebra has a geometric description. It can be described as the space of GLN opers on the punctured disk. So these are some principal G bundles with extra data. But this Fagin-Frankel center, it in fact also admits a very nice explicit algebraic description due to Chervov and Molev. So if we consider the vacuum module for affine GLN, it can be endowed with the structure of a vertex algebra. And then the center can be described in terms of Fourier coefficients associated to vertex operators. And this description, and there are some explicit generators, and this description is not so different from something that is much more familiar, namely the description of the center of the universal enveloping algebra in the finite semi-simple case. So we take this matrix. So this has coefficients in this extension of the affine Lie algebra by this derivation tau, and we can take traces of powers of this matrix, and then they are polynomials in tau. And so we're interested in these in this last coefficient s, and it turns out that this guy lives in the center of the vertex algebra. And the center of the vertex algebra can just describe as a polynomial algebra generated by translations of these Segal-Sugawara operators. And then the center of the completed universal enveloping algebra can be described as a certain completion of a polynomial algebra generated by the Fourier coefficients associated to these Segal-Sugawara vectors. I would also like to mention that the center has a Poisson structure, which is given by the Hayashi bracket. Okay, and so now coming back to the Cherednik algebra. So here we have the definition. So we have these. So it's a quotient of this semi-direct product of the with these non-commutative polynomials where the x's and the y's commute. Then we have these two relations depending on whether I equals j or I is different from j. I'd like to recall a few facts. So first of all, we have this PVW type theorem, which says that the associated graded is just this Q group ring, and the associated graded of the center, these are just the diagonal invariants. Moreover, the ordinary invariants are inside of the center. It's a free module of rank n factorial. And moreover, every simple module has dimension, it is finite dimensional, and it's isomorphic to the regular module of the symmetric group as an ascent module. And every simple representation is determined by its central character. So there is this bijection between isoclasses of simples and the maximal spectrum. And there is also a Poisson structure. There is also a Nakajima quiver type, Nakajima quiver variety type description of the spectrum of the center of the Cherednik algebra. So I take this, the double of the Friend-Jordan quiver with dimension n and 1. And so I consider this space of representations. I have the GLN, which is acting in a Hamiltonian way. And I have this moment map. If I take the fiber at minus identity and take the quotient, then this is the Calogero-Moser space. And by a theorem of Ettinghoff and Ginzburg, this is, we have this isomorphism. So now the Suzuki functor. So the Suzuki functor, I'd like to very briefly explain the construction. So I take a smooth module, then we have an action of the current Lie algebra on this tensor product space given by this formula. And I take the space of coinvariance. So this is very similar to what I mentioned at the very beginning with respect to Schroeval duality. And this has a natural structure of a module over this Q group ring where the x's are just acting by multiplication and Sn is acting by permutations. So the only difficult thing is how to extend it to an action of the whole Cherednik algebra. And this is done by using this Knizhnik-Zamolodchikov connection. So this is this derivation plus a certain second order Segal-Sugawara operator, which can also be described by an explicit formula. And we have some adjustment coming from the Dunkel embedding. And the first observation is that this, in fact, makes sense for any level. So if, in particular, the level is spherical, then we just don't have this, differentiation part. And secondly, it can also be extended to all modules over U hat by taking some inverse limit construction. And the basic properties are that this functor is, so it's right exact, and we have these Verma modules for affine GLN and Weil modules, and so this this functor sends them to it sends Vermas to Vermas, and it also sends Weils to Vermas for the Cherednik algebra. Now the question is, what is the relationship between these two centers? And so in general, the problem is that the functor does not induce, it's not functorial, so it does not induce a map between centers of categories. However, we have a map from both centers to the endomorphism ring of the functor, and it turns out that this second map here is in fact injective. So I define this concept of an F center of a category, which is the pre-image of this second center under alpha. And so the first question is, what can we say about it? And secondly, can we find a subcategory such that when I restrict this map alpha and I consider the endomorphism ring of the restricted functor, so I forget all the modules which are not in my category A, can I find such a subcategory such that the image of this restricted map is precisely the center of the Cherednik algebra? So in practice, this means that I would like to find a map between the centers, ideally surjective, such that all the maps between endomorphism rings factor through this map between the centers. And so we have partial answers to these questions. Regarding the first question, we know that the subalgebra of the center, which is generated by first order and second order Segal-Sugawara operators, so not all of them, but just these Fourier coefficients lives in this F center, and there is an induced map to the center of the Cherednik algebra, which is Poisson. So the Poisson structure on this is essentially a semi-direct product of half of the Virasoro with half of the Heisenberg. Regarding the second question, we can in fact find such a nice subcategory that makes such a diagram commute. And the category which I consider is this category which is projectively generated by a module which is taken to the regular representation of the Cherednik algebra by the Suzuki functor. And so I had these maps from the Fagin-Fraenkel center to the endomorphism ring of H, which goes to the opposite of the rational Cherednik algebra. And it's relatively easy to show that the image lies in the center. We can also show that the image is precisely the center by considering some associated graded argument and a very explicit calculation with these Cherybov, Molev, Segal-Sugawara operators. And so in fact, the Suzuki functor induces, restricted to this category, projectively generated by H, it induces a surjective algebra homomorphism between the two centers. So this has so this allows us to say a little bit more about the representation theory. So in particular, we can deduce that the homomorphisms between the endomorphism rings of these Weil modules and also the Verma modules are surjective. We can also deduce that every simple module for the Cherednik algebra lies inside of the image of this functor. And moreover, there are these restricted Verma modules, which were defined by Arakawa and Fiebig. So you basically take a Verma module and you, so the positive part of the Fagin-Fraenkel center kills it, but the negative part does not. So if you quotient by the action of this negative part of the Fagin-Fraenkel center, and then you get the restricted Verma module. And so these are sent to simple modules over the Cherednik algebra. Okay, and so so now regarding obviously now we have a map between an algebraic map between the two centers, and there is some geometry associated to it. So the question is, can we give some more geometric description? And the answer is that partially yes. So we get an embedding from the Calogero-Moser space into the space of opers, and we can say a few things. So first of all, the image lies inside of opers of singularity of order at most 2. So these opers, you can think of them as some conjugacy classes of differential operators, so that they have a certain order. And so so all of them will have singularity of order at most 2. And we also have a map. So as I mentioned before, there is these symmetric polynomials in the Y's. They live inside of the center of the Cherednik algebra. So there is a map from the Calogero-Moser space to this this quotient. And so each fiber is a disjoint union of some. Is there a question? Or?
Yes, sorry.
Yeah.
I can't go back on the slides, unfortunately. So so this Calogero-Moser thing, is it the spec of the center of the rational Cherednik algebra?
Yeah, exactly.
But you said you didn't. I thought a couple slides ago you said you didn't know if the map from the center at critical level to the center of the Cherednik. Well, you didn't know that your F center was the whole center.
Yeah, okay, so yeah, maybe I went really quickly over this. Yes, so I was making somehow 2 points. I had these 2 questions. So so this F center, this is like the genuine part of the center which really works nicely with the functor. And this is certainly not the entire Fagin-Frenkel center. So if you consider some weird modules, then they don't, the center doesn't act nicely on them. However, and so we have this theorem that is just this this part of the center which is generated by some of the first order and second order Segal-Sugawara operators that is in this F center. And now there is this second question: if we can find some smaller subcategory such that, so when I take a smaller subcategory, I have a map from the Fagin-Frenkel center to the endomorphism ring of the restricted functor. So I basically forget about what the center does on all the modules which are not in my subcategory A. And I would like this subcategory to be chosen in such a way that the image of this restricted map is the entire center of the Cherednik algebra. And so so this map that I was talking about at the very end and saying that it induces an embedding from the Calogero-Moser space to opers, it's this map which is coming from the answer to the second question. Yes, and it's this map that is basically constructed using this module H, which is sent to the regular representation of the Cherednik algebra. Is this clear somehow, or?
Yeah, okay, that makes sense. Thanks.
Yeah, okay. Yeah, so, okay, and so this Calogero-Moser space, it can be, so I was saying that we have this map, pi, and then each fiber is a disjoint union of some affine cells, which can be identified with supports of some generalized Fermat modules. And so we can also say, for example, that the support of Fermat modules goes to, under this embedding, and goes into opers with trivial monodromy and a residue determined by lambda. So here I guess, as I said, it's just a partial geometric description. So, for example, it's interesting that both of these spaces admit sort of Hamiltonian reduction description. So the Calogero-Moser space, I mentioned this, but the opers can also be constructed in terms of the Drinfeld-Sokolov reduction, and it would be nice if one could somehow explicitly connect the two. However, I could never find a way to do this. So yeah, I guess I'll stop here because my time is over. Thank you very much.
Thanks.
So let me make sure, yep, everyone can unmute themselves. So people should feel free to open up and ask questions.
Yeah, I have a question. Can you tell us a little more about this module H?
Yeah, sure.
Thanks.
Right. What was this? Yeah, so it's a slightly artificial construction because it's defined explicitly in such a way that the image is the regular module. So you take, oh, sorry, there's some feedback loop. So you define it explicitly as a quotient of the universal enveloping algebra by some ideal. So you have to kill everything that lives. So you have to somehow take a quotient with respect to a left ideal, which is generated by everything that lives in degree over 2 in G hat, and you also kill everything that is not on the diagonal in degree 1, and you also have to, I think, kill something that lives in degree 0, and yeah, so it's a slightly artificial but explicit construction.
Thanks, that's great.
What, can you say something about this map from the Calogero-Moser space to the opers?
Yeah.
Embedding?
Sorry. Yeah. Yes. So as I said, so we can say something. I mean, there isn't so much we can say explicitly. So, for instance, it would be nice, for instance, if I could take this Nakajima quiver variety description and get a point in the Calogero-Moser space and explicitly construct an oper, but it doesn't really work like that. So there is, maybe I can say the following. So the dual description, so that this map from, this algebraic map from one center to the other, this description is quite explicit, at least at the level of the associated graded. So I went really quickly over this, but I consider this non-standard filtration because it's not really the PBW. I sort of put the elements in G hat, which is tensored with, let's say, TK and T minus K. They are both in live in degree K in this filtration. And so, and then I really, describe the associated graded of this map, and this can be done really explicitly. And one can say exactly where some of the Sugawara operators go. So for example, these shifts of the identity elements, they go to symmetric polynomials in the axis. And there is also an explicit formula for these second order Sugawara operators, which is some polynomial, mixed polynomial in x's and y's. But these higher order Sugawara operators, they're quite complicated. So there is, I just have a description for at the associated graded level, and they go to some power sum type polynomials. However, so there is a relatively explicit algebraic description here, that the geometric one is somewhat lacking. So I can really just say that something about the order of the singularity, and I can say something about the residue and the monodromy in terms of where these cells inside of the Calogero-Moser space are taken, but somehow, unfortunately, that's just it.
This isn't really a question, but can you just, if there's time, can you explain the construction of the Suzuki functor again?
Yeah. Okay. So you take this natural representation of G, and you take the dual, you tensor it n times, you tensor it with your GLN module, and then with polynomials in the axis. And then I have an action of this currently algebra, which is given by this formula. So on these factors, I'm just acting through the, so the y is from G, and I'm multiplying by x. And then here, this is the action on the GLN module, GLN hat module. And then I take the space of coinvariance with respect to this currently algebra action. And so to define, so the Cherednik algebra is generated by these x's, these y's, and the symmetric group. And the x's, they're just acting by multiplication. The symmetric group permutes the x's and the factors in this tensor product. And so the only complicated thing is how to define the action of the y's. And so this Cherednik algebra, it admits this Dunkel embedding into a certain localization of the Weil algebra or whatever the skew semi-direct product of a Weil algebra with Sn. And so so this Knižník samoločík of connection, it defines me a representation of this extended localized Weil algebra, and it's given by this formula, which so maybe what is confusing here is that this Segal-Sugawara operator here, it doesn't make so much sense in terms of this description, because there is also a more complicated space of coinvariance, which is isomorphic to it. And there, this action of the Segal-Sugawara operator really makes sense. However, you can compute by an explicit formula how it acts on this space of coinvariance, and it's this rather ugly formula. And then what you do, you just use this Dunkel embedding, and it turns out that the y's in your Cherednik algebra, they're acting by this Knižník samoločík of connection plus some adjustment. I hope it's to some extent understandable.
Okay, so the next talk will be on the hour, whatever your hour is. And until then, you can chat amongst yourselves.